no need to wait someone because we have audience. And it is really my great pleasure to introduce Andrea with her very interesting mini course in the frame of our lecturum on algebraic graph theory. And she is going to give 3 lectures starting from today, each Tuesday. So this week and 2 coming weeks. And so totally we have 3 talks by her. And just for a brief introduction. So Andrea obtained her PhD thesis at the University of Zagreb in Croatia, and her supervisor was Professor Dean Kronovic, and then later she had been employed at the Department of Mathematics of the University of Rijeka. And now, as far as I know, Andrea is still assistant professor at this university, right? Yeah. So the title of her mini course is Construction of Combinatorial Structures from Finite Groups, and I think it is enough to say that Andrea, it is time to start your first lecture. So thank you very much for joining us and for giving this lecture.
Okay, I'll start to share. I am disabled to screen sharing. It says for me, host disabled participant screen sharing.
Already,
it's better to allow to Andrea to be able to share her screen.
How do I do that?
Look to the green icon in the lower of the screen.
It's done. Sorry.
Yes.
Okay. I think that I can. Just a second. Okay, it's fine. Do you see it?
Yeah, we can see it. Yeah, everything is fine. Yeah.
Just a second. I think it's fine. Okay, so it's fine. I can start.
Yeah, sure, please.
Okay, thank you. So, hello everyone. Thank you very much for attending my talk. And I would like to thanks to Elena for inviting me to participate in this very, very nice seminar. I am really grateful that I can be part of it, and I really hope that you will enjoy my talks. Okay, so as Elena said, the title of my lectures, all 3 lectures, is going to be Construction of Combinatorial Structures from Finite Groups. So in each of the talks that I will present you, I will speak about combinatorial structures, especially designs and graphs that are constructed somehow in a relation with the groups. Okay, so my talk, my lectures, not today talk, will consist of 3 parts. So today I will speak about transitive combinatorial structures, or in other words, I will in details explain you one construction method that you can use for obtaining combinatorial structures that have a property to be transitive. In next Tuesday, I will speak about construction of non-transitive combinatorial structures. And in the 3rd lecture, I will give you applications. By applications, I mean mostly mostly application to graphs. To codes. So in the last part, in the last talk, I will speak about relation with codes on designs and graphs, and how one can use construction that we were describing in the first and the second part by constructing some codes with nice properties that are then good for applications. Okay, so today's talk will consist of, I can say, 5 parts. So the outline of the talk is as follows. So in first part, I will give you basic definitions and preliminaries. In the second part, I will speak a little bit about the history in a way that I will just point out some of the studies that were really somehow connected with the construction method that I will explain you in the third part. In the fourth part, I will show you some nice examples, and in some way I will show you how the construction method that I will explain you in the third part can lead you to obtain a very nice results. And in the fifth part, I will just try to tell you what could be and what are still some open problems on which one can work on. Okay. So let us start. So I am very grateful that Stefan gave 6 lectures before me, because the main topics in, I think, first 3 lectures for him were permutation groups, actions, and these are all things and all definitions that I will need today. Because of that, I will not repeat all the theorems, all the proofs and everything, because he already has done that and helped me with that. I will try to define or at least remind you on some things that he defined very detailed in a way that we can repeat what is needed for further understanding. Okay, so first of all, in today's talk, we will speak about the permutation groups. And what is the most important definition here is the action. So we can define an action of a group on a set. So let G be a group and omega be a non-empty set. The mapping from G times omega to omega defined in this way is an action of a group G on a set omega. If we have that 1 point alpha is equal to alpha, where 1 denotes the identity element and alpha is going through the elements of the set omega. And if the second condition is satisfied in a way that you have that G1 point G2 alpha is equal to the group operation G1, G2, and then acting on alpha for all elements alpha from omega and all G1, G2 from group G. If we have that the group G is acting on omega, then we will call the set omega a G set. And of course, the group G is said to act on omega. So in my talk, I will mostly, maybe in one slide in which I will emphasize you that, but mostly I will use the label G alpha to be an image of the action of a group G on a set omega. If I remember correctly, Stefan did not use this label. He was using this label, alpha up to G. I will not use the same label because I will use this label for special action by conjugation that I will describe you later. So in the literature, depending which literature you are reading, images of the action are differently labeled. For example, alpha G, if you go to Dixon, there is alpha G. If you go to Cameron's book, Permutation Groups, you have G alpha. But for purposes of the construction method that I will show you, I will use the label G dot alpha. Okay, so the most important definitions that are connected with action of a group G on alpha are definitely stabilizers and orbits. So if you have that a group G acts on the set omega, and if you take an element alpha from the set omega, then you can get the special subgroup, which is G alpha. In such a way that in G alpha there are elements of the group G such that they are fixed, G alpha is equal to alpha, and this subgroup is called the stabilizer of an element alpha. We can define an orbit of an element alpha under the action of the group G to be the set of all images of the element alpha from the set omega. Special actions that can occur and that are very important for today's talk are at number one, transitive action. So why? Because I will speak and I will show you the method for constructing structures that have a property to be transitive. So we say that the group G acting on a set omega is said to be transitive on omega if it has only one orbit. So actually it means that G alpha is equal to the whole set of omega, or in other words, for every pair of points from the set omega, there exists an element of the group that will map one point, for example, alpha, to another point, beta. The trivial example of transitive action is the example of an action of a symmetric group defined on n elements and acting on set omega. It is easy to see that for all elements from the set omega, there exists a permutation from a symmetric group such that this permutation will permute one to the element of omega. Therefore, there is only one orbit which is equal to the set omega. Actions that are necessarily connected with transitive actions are K-transitive action and primitive action. So K-transitive action is defined as follows. If G is the group that is acting on the set omega, and if you have K to be an integer such that it is greater or equal to 1 and less or equal to the size of the set omega, we can say that a group G is K-transitive or is acting K-transitively on the set of omega if G is transitive on the set of K tuples of omega. Okay, and primitive action is action that is a necessarily transitive action, but with one extra property. So definition of primitive action is something that Stefan really went into deeply. So it can be defined with the blocks of imprimitivity. But here I will use the characterization of primitive action in a way that I will define in our work the transitive action to be primitive if stabilizers are maximal subgroups. So if I have a transitive action for which stabilizers are maximal subgroup, I will presume that this action is a primitive action. So here we must emphasize that any primitive action is of course transitive one, but every transitive action does not have to be a primitive one. It will be if this extra condition is satisfied. Okay, so the other basic definitions that are connected with today's talk are incidence structures. So an incidence structure is an order triple D where P and P are non-empty disjoint sets and E is a subset of Cartesian product of P and B, or E, we say that E is incidence relation. Elements of the set P are called points, elements of the set B are called blocks. Okay, so the incidence structure can be anything that has these properties. But those incidence structures in which we are interested are designs and graphs. Okay, one very important group that is connected with incidence structure is the group that is called the full automorphism group. How it can be defined? So an isomorphism from one incidence structure to another is a bijective mapping of points to points and blocks to blocks, which preserves incidence. And when we have an isomorphism from an incidence structure D onto itself, it is an automorphism of the incidence structure. So if we take the set of all such an automorphisms, it forms a group which is called the full automorphism group of incidence structure. This same definition of the full automorphism group can be then applied to the full automorphism group of the graph or the full automorphism group of the design that I will speak about today. Okay. The first combinatorial structure or incidence structure that we will be interested in this talk are TVector lambda designs. So the definition of TVector lambda design is that it is a finite incidence structure D satisfying the following requirements. The set P has V elements. Every element of B is incident with exactly K elements of P. And every T elements of P are incident with exactly lambda elements of B. So whenever finite incidence structure has these three properties, then we say that it is called a TVector lambda design. So some properties that are connected with TVector lambda designs are that every element of P is incident with exactly R elements of B. R can be calculated. It is equal to lambda V minus 1 over K minus 1, and it is called a replication, usually called a replication number. The number of blocks is denoted by B, and if B is equal to V, or equivalently K is equal to R, then the design is called symmetric one. So when T is equal to 2, then this design we call a block design. Important property of the designs is the fact that if you have D to be a T design, then it is also an S design for S greater or equal to 1 and less or equal to T minus 1. To each design, we can, for each design, we can obtain an incidence matrix which is a 0-1 matrix having ones on the positions where I and j point are incident and 0 otherwise. One remark in the definition of T-design is the following. So you can see that definition of T-design actually allows B to be a multiset. In other words, we can have by a definition that that we have repeated blocks. But if this is not the case, if B is a set or it doesn't have repeated blocks, then design is called a simple design. So in that case, we can represent a design with points, and blocks we can make with the defining relation to be inclusion. In that way, here is the picture of the design that I showed you in the previous slide. This is the very, very famous design. It is called Phanoplane. It is a symmetric design and it has parameters 2, 7, 3, 1. So it has 7 points, 7 blocks, and in each block there exist 3 points. And it is in some way like a basic symbol of definition of the design in each book of the design theory, where you have a definition of design. There will be a Phanoplane, because it is also very, very nice little design. Okay, as I said before, important property of TVector lambda designs is the fact that if you have a design to be a TVector lambda design, then it is also an S design for S smaller than T. But moreover, you have that it is not difficult to calculate the parameters VK lambda S for this S design. So this formula holds. So if you have a TVector lambda design, then you can calculate what would be parameters also lambda S for S design. I won't write down the proof of this, but I will just give you the sketch of the proof just to have a feeling which kind of proofs are in the design theory. So not all of them, but some of them. So this proof goes very, very easily by double counting. So what we will count, so we can fix S to be and subset of the set of points that has S elements. And we can say that lambda S is the number of blocks containing these fixed S points. So we will calculate the number of ordinary pairs TB such that S is inside the set T and T is contained in blocks of the set of the block of our design T, and set T is having T elements. So double counting by cardinal T and by blocks B, we will obtain the formula that is given in this condition. Okay, so why I am emphasizing this property of T-design? Because I will show you in the construction method how one can use this very, very nice property of the designs. So it actually means that if you have, for example, 3 design, then this 3 design is also 2 design. But if you have a 2 design, it does not mean that this design is a 3 design also. It can be, but it is not following directly. Okay. The history part of my talk. So before speaking about history, I just want to remark here that while constructing, so when you have designs, when you can calculate a lot of variables for designs, for example, parameters, and what will be lambda, what can be r, or etc. But the thing is that you can calculate and you can have the parameters that are admissible parameters, but it does not mean that this design with these parameters will exist. So this is a beauty of design theory, in which, in sense, you know for some of the parameters, but it is a challenge that you construct this design. It is very nice when you have on the paper admissible parameters, and you can really have, in physical sense, you constructed these designs, and this design really exists. So this is one of the basic directions in the studies in design theory, in which people are interested in constructing designs with particular properties. Okay, but I will show you how this idea can be seen further. Okay, so first historical date that I can say it's was very important for the construction method that I will show you is definitely the work done by Matteo. So in 1860, Matteo found first simple sporadic groups, and they were named Matteo groups, and they are multiply transitive permutation groups on 11, 12, 22, 23, or 24 objects. And whenever you try to find in history some first historical evidences of constructing designs from groups, this is something that usually appears very quickly. So they are labeled M11, 12, 22, 23, 24, and they are of size, of this size. So M11 is the smallest and M24 is the biggest. In 1938, Witt gave a construction of Witt designs, and he constructed it from Matteo groups. Witt designs are actually Steiner systems. But what are Steiner systems? Steiner systems are designs with the property that lambda is equal to 1. So you can have TVK, but always you have that lambda is equal to 1. And they are usually labeled with STKV rather than TVK1. You can label them, but in literature they are usually labeled in this way. So actually, Witt gave a construction of Witt designs from Matteo groups. So these 5 designs were called Witt designs, are having Matteo groups as their full automorphism group. But not just that. Matteo groups are multiply transitive groups. And they are multiply transitive groups on 11, 12, 22, 23, 24 points. But they are 4 transitive, 5 3, 4, and 5 transitive. So they are giving, or with constructed Steiner designs that are 4 design, 5 design, 3 design, 4, and 5 design. So you can see that from multiple transitive group, in this case, from 4 transitive Matteo group M11, with constructed 4 design with parameters 4, 11, 5, 1. So it is very, very nice how from these nice groups, which are simple groups, not just simple, but sporadic, multiple transitive groups, you can obtain nice designs. For the second study that I will just quickly tell you something about from the history. Before that, I will just give you a definition of two structures that are connected with a design. As their sub-designs, they are derived design and residual design. So how they are defined? So if you have, derived design and the residual design are defined just when you have a symmetric design. So when you have a symmetric design with parameters 2, vk, lambda, you can fix a block B in this design, and then you can take all the intersection with fixed block B and with the rest of the blocks from the set of blocks, and this will form you a design that will have a point set, all the sets that are on your fixed block B. The size of the block will be lambda, because each 2 blocks are in the present design intersecting in lambda points, and every 2 points will now be together in lambda minus 1 blocks. And this design will be called the derived design of design D with respect to block B. Residual design is defined in the way that you take again fixed block B, but now you are taking differences between blocks from the design 2 vk lambda design minus your block B. It will form you another design that will have a point set to be all the sets minus the points of that are on the block B. They will consist of k minus lambda points each block, and the remaining lambda will remain the same as in initial design. And this design is called residual design of your starting design with respect to B. Actually, if you take a look on the definition of the derived design and residual design, and if you have incidence metrics on your picture, then if you put on the last column, if you name it V times B, and your last column is your fixed block, then actually you can see that one part of incidence matrix will be part of incidence matrix of derived design, and other part will be of the residual design. So these are 2 designs that are connected with symmetric designs. Okay, why? Another thing that I wanted to tell you here, you can see that D is defined X B. It means that we are assuming that incidence relation is actually defined by inclusion. Okay, so why did I define this? Because in this very nice paper by Parker and Tunchev, they gave actually they constructed a symmetric 2 design with parameters 176, 50, 40, on which the Higman-Sims group acts as a 2 transitive automorphism group. Actually, in this paper, they were interested in linear codes. So they were constructing codes from this design, but they particularly emphasized 2 designs. One is residual design of the Higman design, and another is derived design of the Higman design. And both of these 2 designs have nice properties. Residual design have the property that unitary group U35 semi-direct with Z2 acts 2 transitively, and derived design have the property that the same group acts as a rank 3 group. If you remember from the last talk, I think the last talk of Stefan, he gave a definition. What does it mean that the group is rank 3? But in quick words, we can say that a group is of rank 3 if the stabilizers of the elements have 3 orbits. I will show you, we will come again on the rank of the group when we will define paired and self-paired orbits that will connect us to the graphs. Okay, so this is a very nice paper in which application of groups are made for obtaining nice results. And then in 1999, Held, Hrabier, De Angelis, and Pavčević gave a construction of symmetric 36-15-6 design from group PSP for 3. And then in 1999 and 2000, separately, Lambda and Wirth constructed these they constructed, I think in total 4 symmetric designs with these parameters. Lambda constructed 2 new symmetric designs, and Wirth constructed in his dissertation more of them. They are non-isomorphic, but what is very nice is that they both use the action of the group M11 on 144 points to obtain these designs. So, of course, I'm again emphasizing here that these are just few studies that I am pointing out here, because these studies were, in a sense, related to the construction method that I will now going to speak about. 2 papers that are also in a part of the historical pointings out studies are the following. So Key and Muri in 2002 gave a paper in which they gave a construction method for constructing symmetric designs. But the thing is that with this method, you can construct primitive symmetric designs. In other words, symmetric designs on which the full automorphism group act primitively, but also not all of the primitive and symmetric designs, but you can construct those for which a stabilizer of a point and the stabilizer of a block are conjugate. A little bit later, Cimkovic and Mikulic generalized this idea of constructing this idea from Key and Muri in a way that they gave a construction method of primitive designs. So with their method, you can construct not just symmetric primitive design, but all primitive designs. So you can start from a group, and from this group, you can obtain all designs on which this group act primitively. And this leads us to the construction method that I will try to explain you today, and that I will try to show you how you can use for obtaining the results. So this construction method is described by a theorem, but I will go slowly through the most important parts. So let G be a finite permutation group that is acting transitively on the sets omega 1 and omega 2, which are of size m and n respectively. So you have a group that is acting transitively on two sets. If you take element alpha from the set omega 1, and if you define delta 2 to be a union of G alpha orbits, where delta I are representatives of distinct G alpha orbits, then if you act with all the elements from the group G on that defined set, you will obtain a one design. Okay, so the idea is very natural. You take actually orbits of the stabilizer, you act with an element if all the conditions are satisfied, and you obtain a one design. This one design, for this one design, you immediately know what are the number of points, what is the size of the block, and what is lambda. And what else you know that you have a transitive action on points and blocks of the design. So you know that the group H, which is a quotient group of G and intersection of stabilizers Gx, act transitively on points and blocks of the design. Okay, so I will not go into proof by details, but I will give you a sketch of the proof. Again, I am here grateful to Stefan, because all the things that I was using as tool, like formulas for number of orbits, etc., he already proved in the lectures. So I will just remind you. So what we need to prove in order to prove this theorem? First of all, we need to prove that the structure obtained in this way is one design, and that it is the one design with this property. And the third part is that you have to show that this group acts transitively. So clearly the number of points is equal to the number of elements of the set omega 2, because the set of points is defined as it is. The second part, what we know that the set of blocks consists of these elements. So actually, we know that each of these elements is representing a block. So the block has elements as set G delta 2 has. But you can define a bijection between the sets G delta 2 and delta 2. So it means that the sets G delta 2, where G is an element from the group G, and delta 2 have the same cardinal number. So it means that the number of elements on each block is equal to the number of elements in the orbit delta 2. Okay, for obtaining the number of blocks, first of all, we need to see what is delta 2. Delta 2 is a union of G alpha orbits. So, okay, so if you take that, if you take an element from a G alpha, from a stabilizer G alpha, by the property of the definition of an orbit delta 2, you will get that G delta 2 is equal to delta 2. But this means that element G is not just in G alpha, but it is also in the stabilizer of an orbit delta 2. So actually, it means that G alpha is the subgroup of the stabilizer, setwise stabilizer G delta 2. Okay, so if you're counting the number of blocks, it will be the number of elements in G delta 2. But the number of elements in an orbit G delta 2 is equal to the fraction of the number of elements in G and number of elements in G delta 2. You can write it as, you can extend this fraction with this element. And what will you get? You will get that G, number of elements of G over number of elements G alpha is actually equal to the number of elements in omega 1. Why? Because the group G is acting transitively on the set omega 1. G alpha and G delta 2 are remaining. What we know? We know that here we have M elements. We know that G alpha is a subgroup of G delta 2, so we are sure that number of blocks is less or equal than M. Okay, when it is very, very legitimate to ask when it will be equal to M. It will be equal to M when these two stabilizers will have the same number of points. And when it will be when stabilizers are maximal subgroups. And this is the case when you have a primitive action. So this is, here you can have also hidden primitive case in which you will obtain that the number of points is actually equal to the number of elements of the set omega 1. Next step of the proof is to show that actually you really have one design. So that really you have that each point is contained in a constant number of blocks, but not any constant number of blocks, precisely this number of blocks. It is not difficult to see. And then after showing that, that this is definitely true, you can use your formula BK is equal to VR, and you can calculate what is the replication number of this design. The last part for showing is showing that you have H, which is of this type, to act transitively on points and blocks of the design. For this, important thing is to show that actually this is this have the structure of the group, and this will be a group, not a set, if the intersection of all the stabilizers when he's passing on a set omega 2 is normal subgroup. And for that we needed some extra lemma, which is not difficult to show. That with this property we have that the stabilizer is normal subgroup, and then it is easy to see that any element from this set fixes the points in the blocks of the design. So it means that give rise to trivial automorphism of the design. We needed trivial automorphisms because we want that this group acts faithfully as an automorphism group on the constructed design. And this was just a sketch of the proof in which I just wanted to emphasize you how this action of the group is important. What this theorem actually gives you, it gives you the fact that if you know that a group G acts transitively on the points and the blocks of one design, then you can obtain it as described in the theorem. This theorem gives you, in other words, all one designs on which the group acts transitively. But it does not give you two designs on which the group acts transitively. Some of these one designs may be two designs also. So with this method, in order to obtain block designs, we have to make some basic steps. Why? In order to obtain block designs, because when it is very nice to see action of the groups on the designs, also onto one designs. But when you are working in design theory, the designs that are interesting are two designs, three designs, and even more if you can construct them. So in this construction method actually lies the following steps. You have, in order to obtain block designs, you have to determine the set of points. You have to make a list of all possible base blocks that are possible blocks for a block designs. And of course, you have to solve the problem of huge number of constructed designs with same parameters in order to obtain block designs. Of course, you always have the question whether some of them are isomorphic or not. For example, this is a very, very easy example how one can construct Fano plane with this construction method. So you start with a group G, which is isomorphic to L32, and it has 168 points. And if you take H to be a subgroup of the group, that is isomorphic to S4. So for getting transitive action, we can consider the action of G on the cosets of the subgroup, because we know that this action is transitive. And you can calculate the orbits of the stabilizers obtained with this action and take an orbit that has three elements. Acting with the elements of your group, you will obtain a design with this property. So this is an easy example in which actually you can see how one can obtain or can construct a design in this manner. Special case of the construction is the following fact. So if you take subgroups of a finite group, for example, let it be H1, H2, and G to be subgroups of M, we know that group G acts transitively on the conjugacy classes. So if you take an action by conjugation, and if you define your sets omega 1 and omega 2 as conjugacy classes, then you can obtain one designs in the following way. So the point set will be conjugacy classes of the subgroup H2. The block set will be the conjugacy classes of the subgroup H1. And block will be incident with a point if and only if they intersect in particular group. And if you construct one design in this way, you can define it as D obtained with action of the group G, points and block sets, and incidence relation is defined with a group G1 up to GK. So here we were presuming the action by conjugation. So that's why here you have H1 up to G1. This is the reason when I will, why we were using G dot alpha for an image. And here we have H up to G, because this is a special case of our construction, which reminds us for conjugation. Okay, so now here I will stop speaking about designs, and I will focus in the rest of my talk until the end of the talk on graphs. Why? Because I will show you how one can use the same construction in order to obtain transitive graphs. So to have that, I will just quickly remind you on some definitions that we will need. First of all is coherent configuration. So we can define a coherent configuration on a finite non-empty set omega to be an ordered pair of the set omega and the relation R, where R is the set of R0 up to Rd to be a set of non-empty relations on omega, such that the following axioms holds. So the sum of TRRIs is the identity relations, identity relation where R0 up to Rd are subsets of these sets of relation. R is a partition of omega x omega. For every relation Ri, its converse is also in a set R, and there exist constants Pijk that are known as the intersection numbers of the coherent configuration. And what they are representing, for elements x, y from Rk, the number of elements z in omega, for which xz are in Ri and zy are in Nj, equals Pijk. Coherent configuration will be homogeneous if it contains identity relation. And we will say that R is, and if R is a set of symmetric relations, then coherent configuration will be called symmetric. Symmetric coherent configuration is obviously homogeneous. Why we need symmetric coherent configuration? Because we will define association scheme that were introduced by Bose and Shimamoto to be symmetric coherent configurations. So, and the association scheme with relations R0 up to Rd will be called a D-class association scheme. Okay, with association schemes, the structures that are connected are graphs. So we can define distance regular graphs. So if you take a gamma to be a graph with diameter d, and you can define with delta uv to denote the distance between vertices u and v of graph gamma. And you can define the ith neighborhood of vertex v to be the set of all the vertices of the graph that are on the distance I from the fixed vertex v. We can define gamma I to be the ith distance graph of gamma. That is, the vertex set of gamma I would be the same as for gamma with adjacency in gamma I, which is defined by the ith distance relation. And this can help us to define distance regular graph. So we say that the graph is distance regular if the distance relations of graph gamma give the relations of a D-class association scheme. So it means actually that for every choice of I, J, and K, all vertices that are on the distance K satisfy that their intersection of the neighborhood is of size Pij for some constant Pij k. Distance regular graphs can be constructed by the help of the intersection array, in a sense. So in the distance regular graph, we have that intersection number will be 0 whenever I plus j is less than k, or k is less than this number. So distance regular graph is necessarily regular, and his degree will be P110. And of course, each distance graph is regular, having the distance ki, which is equal Pii0. So the equivalent definition of distance regular graphs is actually the existence of the constant numbers Bi and Ci for E going from 0 to D. And the sequence in which we can represent this type of graph is called intersection array of graph gamma. In today's talk, I will point out one family of distance regular graph that today I will be mostly interested in. So these are strongly regular graphs. We say that regular graph is strongly regular with parameters v, k, lambda, mu if it has v vertices, degree k, and if any two adjacent vertices are together adjacent to lambda vertices, while any two non-adjacent vertices are together adjacent to mu vertices. And usually we can denote strongly regular graph with parameters v, k, lambda, mu by this label. It is a distance regular graph with diameter 2 whenever mu is different than 0, and it has this intersection array. Okay, so here are some of examples of strongly regular graphs. These are strongly regular graphs on which simple groups act transitively. So this is a graph on 27 points, 28, 35, 36, 40, and 45. So they are mutually isomorphic. So in total, you have 6 non-isomorphic strongly regular graphs. On 27, 36, 40, and 45, unitary group U42 acts transitively, while on 28 and 35, alternating group A6, I think, yes, acts transitively. So these were these graphs I made in Mathematica, but we constructed them in some of our works, but they are enough small to have them represented in this way. Okay, so how you can construct transitive graphs. So let us remind on the action of the group G on the set omega x omega. So let G be finite permutation group acting on the finite set. And this action is actually inducing the action of the group G on the set omega x omega. In this action, the orbits are the sets of the form alpha G, beta G. So you see, I here left alpha G. It is the same as G dot alpha. So if G is transitive, we know that alpha alpha is one such orbit. If the rank of the G is R, then it has R orbits on omega x omega. So if we put that the set omega has n elements and let delta I be one of these orbits. Then we say that n times n matrix I, so square matrix, having rows and columns indexed by the set omega, with entries 0 and 1, will be called the adjacency matrix for the orbit. So it will have a 1 on the position where alpha and beta are the elements that are in the same orbit, and 0, it will be otherwise. So you can have A0 up to AR-1 adjacency matrices for the orbits of G on omega x omega. They satisfy the following conditions. A0 is equal to identity matrix if G is transitive on omega. If G has S orbits on omega, then E is the sum of S adjacency matrices. The sum of all adjacency matrices is equal to all one matrix. If E is an adjacency matrix, so it is its transpose. And if you have two adjacency matrices, then their product will also be integer linear combination of adjacency matrices. And if you have that I is symmetric matrix, then the orbit that is corresponding to this matrix will be called self-paired. If further I and Ij transpose, if they are equal, these two matrices are equal, corresponding orbits are called mutually paired. So if you take a look on this construction, let G be a finite permutation group acting transitively on the set omega. Okay, so you have a finite permutation group acting transitively on the set omega, and you have adjacency matrices for orbits of G on the action omega x omega. Let B1 up to B2 be subset of A1, A to D, so to be a set of adjacency matrices for the self-paired or mutually paired orbits. So you are taking self-paired or mutually paired orbits. Then M, which is the sum of these corresponding adjacency matrices, will be the adjacency matrix of a regular graph. And the group G acts transitively on the set of vertices of the graph gamma. This construction is actually construction that is written in a different way and can be easily read from the theorem that I was pointing you out. So this is the theorem in which we have a construction of one designs. But if you take a look on this remark, if omega 1 is equal to omega 2 and delta 2 is a union of self-paired and mutually paired orbits of stabilizer G alpha, okay, so you have that these two sets are equal, and you have that you are taking just self-paired or mutually paired orbits of G alpha, then you will have that your design is symmetric self-dual design. What does it mean? It means that it has symmetric incidence matrix with zeros on diagonal. And that means that incidence matrix of that design is actually adjacency matrix of a regular graph with regularity equal the size of the orbit that you've taken. So actually constructing regular transitive graphs follows from the theorem. we written construction in the way in which we could write it in a way of adjacency matrices of an orbits and via associations schemes. Okay, so this was the things that I wanted to show you for the construction of designs and graphs. So how one can use particularly that explained method in order to obtain results. If you want to say, yes, this method is very nice, you have to prove it in a way that you really constructed very nice examples of structures with the used method. Okay, so here I will point you out results that we obtained by performing the construction method. And here I will just show you those following for constructing of transitive graphs. So we've taken unitary group U for 2, simple group of this order. It has, for your information, 116 subgroups, and up to index 600 there are 40 subgroups. So why this is important for this talk? It is just for your information, but this work is related with classification of transitive graphs from simple group U for 2. We did not obtain the whole classification because it was out of our computational reach. That's why these 40 subgroups are important, because we went up to index 600. So here is information label of those subgroups that lead to graphs that I will show you. And this is information of the subgroups, the structure, the order, index of the subgroup, rank of the group, and information whether graphs are primitive or imprimitive. It means that they are transitive but not primitive. So here you have those 27, 36, 42 non-isomorphic group on 40 points, and 45 those these are connected with the graph that I show you on image. So what we constructed, we showed that up to isomorphism there are exactly 12 strongly regular graphs with at most 600 vertices admitting transitive action of the group U for 2. And here are these strongly regular graphs. So this is the path in which you can see how it is constructed. We started from U for 2 using subgroup H1, obtained strongly regular graph with full automorphism group, this one. They are all nice, they are strongly regular, and by the definition they are nice. But here we obtained these blue ones, and this was something that was very, very nice. Why? Because the graphs with these parameters are very new. So this was the graph that we constructed, and for these parameters we actually proved the existence of the strongly regular graph with these parameters. We've done the same for 540, 187. And why this result was very remarkable, it is a very, very interesting story. We were constructing and we were pursuing and classifying strongly regular graphs from U for 2 as much as we could, because it is a very interesting information if you know which kind of graphs are arising from groups. It means in a sense that actually these graphs or designs are lying inside the groups that you are taking. But in this case, when we've taken this group, we obtain a new strongly regular graph, new in actually in a way that we prove the existence of these parameters. It was remarkable because it is very, very interesting to know that you have a transitive action of unitary group that is acting on 216 points. In very easily obtaining the method, you can construct this graph. I remember when I was constructing this, I was doing this with my colleague Dejan Crnković, and when we obtained this new strongly regular graph, I really was very surprised. I closed all my program and everything because I was sure that I made a mistake. Because when you go on the browser's page and you see that there is a question mark there, and it is not a huge number of vertices, it was impossible that we found a new strongly regular graph. But then we went again into computer, start Magma, and we actually convinced ourselves that we've done everything correctly and that we really constructed this new strongly regular graph. So this was actually a proof that this method that we used was very fruitful, and constructing structures starting from finite groups is something that will always in some way give you nice results. Here you can more about these parameters of strongly regular graphs and more in general about strongly regular graphs. You can find on the web of Brouwer and in the handbook of combinatorial in the combinatorial designs. Okay, so this leads me to the last slide of the talk, which is titled Open Problems. So here, open problems, I can name that always open problem is classification of particular designs and particular distance regular graphs with some property, for example, transitive ones. Proving definitely the existence of transitive T designs and distance regular graphs, and trying somehow to develop method that could give you some results that are very, very nice. Here I emphasize one book that is written by Shirley Pregen and Leonard Soicher. It is a book that consists of the distance regular graphs with low rank representations. I think that they arrived up to rank 5. They gave the whole classification of distance regular graphs from sporadic groups. So it is something that can be extended in a way that you can construct with this method even higher rank representations, and you can make a contribution to the extension of these very nice results given by Prager and Soicher. And of course, always starting to find new strongly regular graphs is something that is, by my opinion, worth of doing. So with this, I will conclude my talk. I'm sorry that I a little bit extended my time. I was not aware of the time. I hope everything was clear, and thank you very much for your attention.
Andrea, thank you very much for your very nice talk. And actually, there's no such strictly restriction, I mean, with timing. So you're welcome to use this time for lecture as you need. So are there any questions to Andrea?
I've got just one comment.
Sure.
A fantastic talk, Andrea. That was really good. I
Yeah.
enjoyed it very much. The simple group you studied at the end, U4 of 2, it's also a symplectic group,
Yeah.
PF243, isn't it? And
Yeah.
it's a very classical example. It's the group of the 27 lines on a cubic surface. And geometers studied this very intensively. About 100 years ago, you'll find old papers and books on the 27 lines on a cubic surface. And you may find that some of these graphs that you've been finding associated with that graph, with that group, they won't appear as graphs in those papers, but the actual configurations may be in there, suitably disguised as configurations of lines and points and so on these cubic surfaces. And you may find that some of these new strongly regular graphs you've discovered are lying almost hidden away in the ancient history of the subject. I think it would be rather interesting to explore that.
Yes, yes, definitely. I am really interested in these graphs, and when we found them, it was remarkable. But we tried to find a lot of information about it, but it was a question mark, and we didn't find anything. So, but thank you very much for the remark.
Okay, well, thanks for the talk.
Thank you.
Really good.
Very good, yeah. Okay, any other comments or questions to Andrea? Well, okay, if not, then let us again thank Andrea for so nice talk and with representing historical background of this topic and for sharing with us new methods and new results. Thank you very much. So we are looking forward in 1 week to get the second lecture. Thank you very much. Okay.
Thank you all for participating.
Yeah, it was great. It was really great. Yeah. Okay. I will send the information about the next lecture, and actually all lectures are recorded, so you will have a chance to have a look on this video lecture one more time. Okay. See you in 1 week.
Yeah.
Thank you. Goodbye.
Bye.
Thank
Thank
you.
you.
Bye.
Goodbye.
Bye. 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 Bye, Dean. Yeah. Okay. Bye.
Bye.
Now. Bye.
Bye.
Bye. Andrea, can you see this flower? It is well. So this one.
Yes.
Yeah. So just today morning.
Okay.